Thanks for the opportunity to talk again. Good afternoon. Today I'm going to talk about a new formulation for the group sparse NMF problem, and also I'll give a coordinate descent algorithm to solve it. Before I go ahead with the formulation, let's quickly review the NMF problem. So what is the NMF problem? You're given a non-negative matrix and you want to approximate it as a product of two low-rank non-negative matrix factors. So if X corresponds to your data, the columns of your X corresponds to your data points, the columns of W corresponds to your features, and H is your representation matrix. All right, so why is this interesting? NMF has a very rich history going back to the 60s, a lot of problems, a lot of fields such as chemometrics, document analysis, and it has a wide range of applications such as collaborative filtering, hyperspectral image analysis, and many others. Usually the approximation is done by the Frobenius norm, but other measures include KL divergence, beta divergence, and the later norms are very popular in the music and speech applications. So the problem is in general non-convex. Though convex formulations do exist, these are much more popular in the document or text mining. So, however, in the general areas, the non-convex problem is preferred. So, if you have additional information based on your domain knowledge, let's say you're trying to analyze fMRI brain imaging datasets, then you might have some prior knowledge from the expert saying that some of your features are going to correspond to certain parts of your brain. So then naturally sparsity constraints will apply in addition to your non-negativity constraints and low rank constraints. All right. So how do we impose sparsity? L0 norm corresponds to your intuitive notion of sparsity. However, optimizing for it is hard. So Hurley and Ricard did a paper in 2009 where they asked the question like, what are the desirable properties your sparsity measure should satisfy? I won't go through all of those properties, but it turns out that Heuer's sparsity measure, which is a ratio of L1 over L2, pretty much satisfies all of these properties except for cloning. And the other nice property of this sparsity measure is that it lies between 0 and 1, 0 corresponding to be totally dense and 1 corresponding to being totally sparse, and all the values in between. Okay. So if you apply this sparsity measure in addition to your, if you incorporate the sparsity constraints to your NMF problem, then you see that you get your usual NMF objective, X minus WH, which is the Frobenius norm, the non-negativity constraints, and these this L2 and L1 constraints are coming from the Heuer's sparsity criteria from the previous slide. And you get you get R of these. And how do we optimize for this? There's a very simple algorithm for it. You just do block coordinate descent, take each feature at a time, and it turns out the objective function is a linear function, and you're just projecting it to a hyperplane and a hypersphere, and you can do that very efficiently in linear time. And in fact, you can compute all the solutions for alpha with an extra log penalty. So you can compute it in log n time for all the values, all the feasible values of alpha. So that's nice, and these are some results which are pretty standard. I'm sure everyone has seen them. With various sparsity parameters with 0.5, 0.6, and 0.75. As you can see, as the sparsity increases, the sparsity of the features it also increases. The nice thing about this formulation is that it is very friendly to the user, because the L0 norm and this translated L1 and L2 kind of map very closely with each other in practice. So that's why it's kind of a nice measure from a user perspective. So what is the bad part of this formulation? It is that all the features have the same sparsity. I mean, in real data sets, it's unlikely that all the features are going to have the same sparsity value. So we would propose a new group sparse NMF formulation where we have our usual NMF objective. We have the norm constraints, which takes care of the L2 norm constraints, which takes care of the scaling problem. And instead of having sparsity for each column, the idea is as follows. We have a bunch of features which map to a group, and you set the sparsity for these groups. Okay. So as an example, think about the faces. You might want to have two groups. One is a global group where the features are totally dense, and a set of local features which are totally sparse. So the global features may capture things like the background conditions like lighting or the general facial mask. And the local features will capture things like eyes, nose, and ears, which are more local. So that's the basic idea. So how do we optimize for this new or this group sparse NMF formulation? Can we use our previous column update? Well, we cannot, because if you just update a column at a time, the sparsity mixes along the rows, but it does not mix along the columns in your feature group. So we need something. So one feature at a time doesn't work. So the obvious thing is to update 2 columns at a time. So in this way, when you update 2 columns at a time, the sparsity mixes along the columns in your group. And the reason we take a disjoint subset is that you still are able to get a linear problem, a linear objective function. Because they're disjoint, the original objective function becomes a linear. And so you have a linear objective, and instead of the L1 and L2, now we have an L1 and 2 L2 constraints. And this can be, again, efficiently computed by just simply computing all the solutions from the previous projection operator with an epsilon net, and then just find the solution which sums up to k. Look for the one which sums up to k. That's the basic algorithm. So since we updated, and the extensions are, we updated 2 columns at a time, but there's no reason we cannot do R of these. But if you do R of these, then it'll end up being it'll be a dynamic programming problem. All right, and then we applied this to just as the illustration on the faces. The left and the middle are where we set sparsity on the whole set of features. As you can see, you get a mixture of global and local features. And the right one is the more interesting one, which, as I was saying, that the top row corresponds to where we set the sparsity to be low. And as you can see, the top row, you actually get a bunch of global masks on the faces. And you see the remaining ones, the sparsities are low, and you get sparsities high, and you get these local features like eyebrows and lips or things like that. So this is just an illustration of the power of this formulation. And we can extend it to other structures like orthogonality and other norms like L1 and L infinity and things like that. Yeah. 5 minutes?
Thanks a lot.
Yeah.